Okay, so here we have a question that deals with an object rolling down an incline and then falling off and hitting a wagon. So it's predominantly a rolling question, but there's a little bit of momentum at the end. So first thing, part A is drawing a careful free body diagram. And it's important to note that since this involves rotation and rolling motion, and as it says in the question, you have to put the forces at the exact points where they're applied. Just drawing them on the object is not going to be good enough to solve the problem. So let's draw. That's our ball. The ramp, right, kind of like that. Then the first and most obvious force is going to be gravity, right, that acts at the center of the mass of the ball. Then the other forces that are involved act at the point of contact, right? The normal force acts at the point of contact, goes right through the center, right? It's perpendicular to the surface, so that's our normal force. And then friction, actually that's kind of it's got to be parallel to the surface. We're just going to call that kind of a cursive F. Actually, I'll go to subscript. F sub F, if I could get that. There. And so those are the three forces. You have to get, just having the forces themselves correct will get you probably just the gravity point, because that'll be right at the center. You don't get points for getting the forces correct and having them all in the wrong spots. So getting the locations of these forces is absolutely critical. Remember, friction and normal force are contact forces, so they're applied at the point of contact. So with that, we can do part B. And part B is definitely the hardest part of this question. And so as with other things, if you end up being unable to do part C and D because you can't figure out B, make up a number for B and then move on. Part B is really the challenge. So our goal is to calculate what the magnitude of that frictional force is. And the way we're going to do this is by remembering what that rolling without slipping statement means. Because that means there's got to be a relationship between its angular or rotational motion and its linear motion. And that's what gives us enough knowledge to actually solve the problem. Because we don't know how fast it travels at the end, that's part C. We don't know how fast it accelerates in total. That's related to the amount of friction that we have, right? If we knew that, we'd know the friction already. And so only thing we can do is start trying to figure out sort of how do we describe this object in terms of Newton's laws. So the first thing we can do is there's the sum of the forces. I'm going to call this in the x direction. But what I mean with the x direction is the down the ramp direction, right? This is x. Oh, that's really sloppy again. Right, that's what I mean by x, is the down the ramp direction. Right, so it's net forces in the x direction that cause acceleration down the ramp, which is what we know is going to happen. And there's two forces that are involved here, right? The normal force is in the y direction as it's drawn, doesn't contribute at all to this. So we only have the frictional force, which is up the ramp, so negative, and part of gravity, right? I'm going to sketch this kind of on. Right. If this is theta, then that is also theta, right? So if we take all that into account, we have the force of gravity, which is mg, and we need the opposite side, so sine theta, right? So that's true, but it's not totally useful because we don't know the acceleration. But we do know there's something else that's true. We know there's rotational forces that cause it to start rolling. And so we can write the net torque, right, the Newton's rotational version. And to solve this correctly, the most useful pivot point, right, since we care about the frictional force, it wouldn't make sense to put the pivot point where the frictional force is applied. Then there'd be no force exerted. We wouldn't be able to solve for anything useful. So the next most logical pivot point is right the center of mass, which means the gravitational force will now exert no torque. And handily as well, the normal force is applied in a line that's parallel, right? That's R for the normal force, and those two are parallel, so the normal force also exerts no torque. So there's only one force that exerts a torque here, and that's friction. So the frictional force times R, and they're perpendicular, so the sign is going to be 1. And now we have the moment of inertia, which is 2/5 mr squared. And now here's where we can use the fact that it rolls without slipping. Since it rolls without slipping, alpha is that AX over R, right? That's the no slip constraint. So we can cancel all these R's out. And we find that the force of friction is 2/5 MAX. Or MA, oops, I should not write that as a subscript. Right, just rearranging. And we see that this right here can be substituted in quite easily, right? And we'll eliminate that unknown acceleration. I changed notations halfway through, which is kind of sloppy, so let me go clean these subscripts up. All I want is the F, not the whole friction thing. Right there. Okay, so we substitute that in, and we get negative right, and now we can just solve for the force of friction, combining the two. So we have 5/2 plus 2/2 is 7/2. And now we just multiply by 2 and divide by 7. And so we have all these numbers, right? The mass is 6 kilograms and theta is 30 degrees. So we can plug these numbers in, and if you do that carefully in your calculator, you're going to get 8.4 newtons is the frictional force. And so if this ball was rolling in some other way, if it was slipping a bit, then you wouldn't know the frictional force anymore. The only reason we're able to do this is because of that statement that it rolls without slipping, which is why that's kind of a tricky way of forcing you to solve it. All right, that's the connection. So for part C, 2 different ways to do it. The first is, if you couldn't figure out how to do part B, you can do part C completely independently. We'll do that one that way first. I think that's the easier way. So part C is really a conservation of energy statement, right? The friction force, since it's a static friction force that causes rolling, doesn't do any work. So the energy before and the energy after are the same. And so if we do that, well, our initial energy is gravitational potential energy, mgh. And our final energy has 2 types, right? It's translational and rotational kinetic. And we'll say that that's, right, the bottom of the ramp is our 0 point of gravitational energy. So to figure out h, right, we have, right, this is h. We know this length L, and we know that angle. So we know that the sine of theta is h over L, or h equals L sine theta, right? So now we've turned that h into something we know the values of, because we know theta and L. So let's put that in. And since we care about the linear speed, I'm going to keep v as it is. I'm going to substitute what I know in for the moment of inertia. And once again, we can use the fact that it rolls without slipping to replace omega with v over r. Right? Since omega is squared, I have v over r squared. So that'll cancel those r squared. The 2's cancel there. We have a mass in every single term. So that cancels. So we are left with this. Right, after everything cancels. So we can combine those v squared terms. So we get 5/10 and 2/10, or 7/10 v squared. And now it's just a matter of solving. So we'll multiply by 10, divide by 7, and take the square root. And once again, we know all those numbers. L is 4 meters. That's the only one that's new in this part. So you plug that in, you get 5.3 meters per second. Okay, so that's approach number one. If you couldn't figure out part B, right, you could do part C completely independently without knowing anything about it. But maybe you were really confident in what you did in part B, and so you were thinking in terms of forces already, right, because you got a frictional force. And so maybe instead of coming with this, you wanted to do something with forces and accelerations and then kinematics to get the speed, right? So we know how far it travels. So that's another possible option. So we know from part B, right, we had, to go back a page on this circle, we had a handy relationship that we came up with right here. A relationship between the frictional force and the acceleration. And now we know the value of that frictional force. We can figure out that acceleration, right? So we could rewrite that. The acceleration is 5 times the frictional force over 2m. And we know all those numbers, right? So you can plug them in. That's really sloppy even for me. So you get 3.5 meters per second squared if you use those numbers. And again, if you got the wrong result in B, but use this relationship correctly with that result and get a different number, that's fine, as long as you're consistent. So we know the acceleration, we know how far it traveled, but we don't know how long it takes. So the useful kinematics equation to us is going to be this one. Right? So V final is what we care about. That's what our unknown is. It starts at rest. The acceleration we just found, and delta x is the real distance that it travels, or that 4 meters on the ramp. And so you can see we can plug all those in and then take the square root. And so we will again get V final is 5.3 meters per second. Either way works. I think the question kind of leads you, if you did part B correctly, it kind of leads you to use the kinematics approach. But if part B is hard, and so if you figured out part C, then you could get part B, you could get it without ever doing part B. Now, it's also important to note, right, if you figured out how to do part C very easily and you got this, well, then you could take this and use that to get this relationship, right? If from before you only recognized this statement right here. So if you recognize that part C correct, you could then use that final velocity to figure out the acceleration you had to have, right? That would be from this right here. Or rather, that would be from this relationship, right? You could solve for A instead. And then you could get part B by doing part C first. If you did that, so like if you never once did what I'm going to box in this purple, if you never once did this, but you still solved it because you did part C, you still get full credit. It's like that would be fine. If you recognize things that work physically, you can do whatever it takes. You don't always have to do part A, then B, then C, then D. Sometimes you can sort of rearrange the order if you can figure out some parts more easily than others. I think part C with energy conservation is easier than part B. And so if I were doing this question the easiest way possible, I probably would have done part C first and then used the result from part C to get part B. Just because I think energy conservation is easier than free body diagrams and multiple Newton's laws equations. So that is a fine solution option. All right, and finally, we have part D, which is the only part that's not really a rotation part, is that we have a wagon at rest at the bottom, and the ball falls, lands in it, hits and sticks, so it's an inelastic collision. And we know the total mass of the wagon and box, and we want to figure out the horizontal speed. So there's a lot of extraneous information here. The first thing to note is it does not matter how far the ball falls, because that's only going to affect the vertical component of the motion. And we care about the horizontal component, right, the horizontal speed. So all we need to do is take what we got in part C and find the horizontal component of that. I'm going to call that V initial x is the final, and we know it's the x component, so the cosine of theta, right? And so that's the 5.3 meters per second times, right, cosine of 30 degrees. So that right there is the horizontal component of the velocity, no matter whether it falls 1 meter, 100 meters, a kilometer, doesn't matter. And since we only care about the horizontal motion, we don't need to use any of that information about how far it falls. And now all we're going to do is we're going to say the x momentum is conserved, right? Because there's no external horizontal forces. Vertically, momentum will not be conserved, right? The ground, the normal force from the ground will exert a force. And so the vertical momentum will not be conserved, but horizontal we're fine with. And so initially, it's just the mass of the ball times v initial x, right? That's what we calculated above. And after, it's an inelastic collision. So they stick together, and they have some final velocity. So we can just easily rearrange and solve. Right. Actually, I'm going to save a little bit of time. And this is just VF cosine theta, right? Exactly what we wrote above. And we know all these numbers, right? The ball is 6 kilograms. The wagon is 12. And so you can punch that into your calculator and you get 1.5 meters per second. And again, if you got the wrong velocity from part C, but you use it correctly with the conservation of momentum statement, then you're going to get the points in part D. Right, so even if you couldn't do any of the rotation stuff, you can get part D correct. And it's also important to note that this question was graded in such a way that there's 3 parts with numerical answers, right? B, C, and D. If you had the right units, no matter what the numbers were, just the right units for 2 of those 3, you got 1 additional point. So if you were completely lost to anything involving rotation, but you could do the momentum conservation, and you made up an answer for part B, you made up an answer for part C, and you did part D correctly, you could get 4 out of 15 points just for that. As long as you got the right units and correctly calculated the conservation of momentum stuff. So as always, don't get hung up on the hard part, because part B is definitely the challenging part of this question, and it appears very early on. But you can do part C and D without needing anything from part B, as long as you sort of don't panic.